Yeah. So as long as you have paid attention and yeah, went over lecture notes, every example we did in lecture, and the quiz problems, you should be fine. Like honestly. I'm not gonna put anything tricky on that. Everything is just gonna be like what I discussed in class. So make sure you kick ass. It's a soothing music, really. Thrash music. It's soothing, huh? All right. Any bets for the test? Yeah, I can bet on something for the test. So this happens a lot when people do a, like, let's say whatever test for convergence or divergence. They say that, so the question is about the summation of a sub n, okay? And you run basic comparison, limit comparison, whatever test you do. In the end, people say, this happens a lot. People say a sub n converges or diverges. They forget that they're dealing with a series, not a sequence. You know what I mean? They do a test on the series and then in the end, they mention a sub n convergent, and that is not correct. Yeah. So let me see the calendar here. Do I have the syllabus on GoodNotes? I don't. Yeah, guys, give me 1 second over here. I can give the test on Monday if you guys want. If you want. Any objection?
No objections.
All right. Yeah, why not? I don't want to make it a stressful test, to be honest. I want you to have fun with it, not have fun studying. So, well, let's do it on Monday. But the quiz is due today. All right. That should be turned in today. Alex. On test two, the test on chapter, what was it, 7, a few students collaborated, and I haven't yet taken any action on that yet, because I'm just so busy with everything. I mean, I tried to do my work, okay, but I haven't yet taken care of those who collaborated on test 2. I don't want that to happen on test 3, okay? I will be calling on those people soon. I haven't had time yet. So if you did collaborate on test 2 on Discord or whatever, you send text, pictures, whatever you did, that is not gonna happen on test 3, because if it does happen, I'll get you for both test 2 and test 3, and you're gonna be reported, okay? Yeah. So let's continue, guys, with the ASC here. Yeah, I've been doing this job for a long time, guys. I know when people work on a question together, I know. Okay, it's not like you can get away with it, really. If two people work together on a problem, it is very obvious. I can show the work from both students to another professor, and they're gonna be confirming that also. So letting you know, directions say you can't collaborate on a test, and you have to abide by it. It's cheating. Okay, so talking about absolute convergence, we said a series converges absolutely again. If when you make all terms positive, then the sum converges. So here again is the definition. It converges absolutely if the sum of positive terms converge. Okay, and we said that if an alternating series converges absolutely, then it is convergent. Just think about absolutely as surely, for sure. The series is going to be for sure convergent, and you don't need to do AST. Okay. If a series is not absolutely convergent, but convergent, then we say, so here we go, like this example, the alternating series of 1/n squared, it converges absolutely, because if you drop the -1 to the end, you get a convergent P series. It's convergent absolutely, therefore it is convergent. You don't need to run the AST. It's going to be a complete waste of time. Okay, that's how you can waste time on the test, on the exam. Check the AST. You don't have to. If you have a series that is not convergent absolutely, but by AST it is convergent, then we say it is conditionally convergent. Like the alternating harmonic series, check for absolute convergence, make all terms positive, basically drop that -1 to the end, you end up with the harmonic series. And we know that the harmonic series is divergent. Okay, so this series is not absolutely convergent. Okay, this series is not absolutely convergent. Therefore, you have to check for conditional convergence. And you do that by running the AST, alternating series test. The two requirements of AST, they pass. So we say the series is conditionally convergent. If it's not absolutely convergent, but it is convergent by AST, then it's conditional. Conditionally convergent. So let's do more examples here. Let's say n goes from 2 to infinity of 1/ln of n to the power of n. And let me make it alternating. There we go. Okay, so again, this is an alternating series because of that -1 to the end. We're going to begin by checking for absolute convergence. Okay, and you do that by looking at the sum here. By the way, n cannot begin with 1. It has to begin with 2, because when you plug 1 for n, ln of 1 is 0, and the sequence function is not continuous. So to the absolute value of the nth term, again, what the absolute value does is that it drops the -1 to the n. and you get 1 over ln n to the power of n. Okay, so this is now a positive term series. Okay, because n is 2, 3, 4, 5. This sequence is the nth term, the sequence of the series is never going to be negative. It's a positive term series, so you treat it as a positive term series. You run one of the tests. What do we have? We have the nth term test, we have the integral test, we have a comparison test, we have ratio test, and we have root test. I want to go with what test, guys, on this? What test should I use?
Root test.
And through.
Yeah, root test, because the nth term involves a power of n. Okay, so we run root test. All right, you're just gonna do the limit as n goes to infinity of absolute value. Well, not absolute value, just limit as n goes to infinity of the nth root of a sub n, nth root of 1 over ln n to the power of n. Okay, again, that power of n drops out and you end up with the limit as n goes to infinity of just 1 over ln n. And we know ln n goes to infinity, and you get 1 over something that goes to infinity, the whole thing is just 0. Okay, and we got L. L is between 0 and 1. It's actually 0, which satisfies this condition. Therefore, this is convergent. Okay, so what we are checking for again is the absolute value of u sub n. This converges. Okay, and that is by the root test. Okay, therefore, the original alternating series converges absolutely. Okay, that's the conclusion. So please look at the argument here. How the argument is like the order of the argument. Okay, so checking for absolute convergence. Look at the absolute value of the nth term. You get a positive term series. Run the test. This test is again on the sum of the absolute value of the nth term. So in the end, you say the sum of the absolute value of the nth term converges. Therefore, the original series is converging absolutely. Okay. And do I need to check AST? No, we are done. If you want to run AST, be my guest. It is a complete waste of time. We know for sure the series is convergent. Okay. Yeah, it's converging absolutely. I'm not going to have to say anything. It's just converging absolutely means convergent. Convergent for sure. So again.
I have a question.
Yeah, question.
Is there another way to write a alternating series without using the -1 to the power of n? Like, is there another like little function or something like that that does the same thing?
Like how? Okay, without that. So you want to express the -1 to the n in a different format?
Yeah, is there a way to do that?
Do you have something in mind?
No, but I was just wondering, just to look out for when we're.
There is not. I mean, you can use a cosine of n pi.
Oh, okay.
But yeah, this is just the most basic format. Yeah, there
Okay.
is no other way.
So we won't see any others except for this one, and maybe.
Right, yeah.
Okay, perfect.
Mhm. There are certain weird series that actually are not alternating always. Maybe I'll do one of those examples from the book. Yeah, let me just finish with my examples and then let's actually take an example from the book. But does anyone want to ask a question from section 11.6 or 11.5 in the book? I can answer questions. Yeah, I gotta look for a problem that is maybe conditionally convergent. Okay, I'll just make something. Make something. Yeah, did you have a question?
Yeah, 13 on the homework.
Yeah, not a problem. 13
Cool,
sounds.
thanks.
13 from 11.5, right? Yeah,
Yeah.
okay. I'm looking at 11.6. That's why I'm all confused. Okay, now it all makes sense. Yes. 13, such a weird problem, huh? I can see why people are stuck on problem 13.
Yeah, it spooked me.
So again, section 11.5, and the series is and going from 1 to infinity. You don't have to even write that. We have -1 to the n minus 1, and then it is e to the power of 2 over n. Okay. So this is an alternating series. All right, and we want to check for absolute convergence, I guess. Yeah, let's do that. Always begin, if you want, by checking for absolute convergence. Okay, so again, we do the absolute value of the nth term. Okay, and this gives us just e to the power of 2 over n. All right. Okay. So we have a positive term series. Oh, yes, Ahmed. We have a positive term series. And again, try to use one of the tests. So the most basic test is the nth term test. You begin by that. You can try and think of other tests like the integral test, the comparison test, ratio test, root test. First of all, I don't want to do root test because I don't have a power of n. We have a power of 1 over n. It's an over n. It's not a power n. Okay. Ratio test, I don't know about that. Ratio test is good if you have multiple factors. Okay, I don't have multiple factors. I just have e to the power of 2 over n. Okay, and then limit comparison test is good if you can come up with a sequence that is asymptotic to the sequence. Okay, so typically, if you have like a rational sequence, like n cubed plus n over n cubed plus 2n, something like that, where you can take dominant terms on top and bottom, that's when limit comparison is useful. Okay, basic comparison, I'm never a fan of that. Integral test, try taking the integral of e to the 2 over x. I don't think we can. We cannot take this integral. It's dx is in the denominator, okay? So I am left with the nth term test. I should have just begun with that. You guys should begin with that all the time. Unless it is apparent what to do from the beginning. Like for this previous example, it was apparent that the root test is the easiest way to go because I have that power of n. But for something like this, if nothing is apparent, then begin with the nth term test, the most basic test. Okay, so we're gonna take the limit. Let me mention that. So use the nth term test. Do the limit. Then goes to infinity of e to the power of 2 over, well, a sub n. That's the limit. As n goes to infinity of e to the 2 over n. All right, don't think about this too much. Just see what happens when n goes to infinity. When n goes to infinity, 2 over n is the part that's changing. The exponent's changing. 2 over n goes to 0. So we have e to the power of 0. Okay, you can move the limit to the exponent. That's what we can do because e to the u is a continuous function. You could move the limit to the exponent, take the limit of the exponent, you get 0, e to the 0 is 1. So what this says again is that when you expand the series, and when you write the terms long enough, terms are going to be eventually very, very close to 1. So you're going to be adding a bunch of 1s forever. And that goes to infinity. So yeah, divergent. This is not equal to 0. Therefore, divergent. So what is divergent? It's, yeah. It's this that's divergent. Okay, so the sum of the absolute value of the sequence is not absolutely convergent. Okay? Yeah, this was a great problem. Not absolutely convergent. So that doesn't mean that the series is divergent. It could be convergent, but not absolutely convergent. So now you check the AST. Okay. Yeah, we check the AST. So we're running the AST again on the series. Okay, there are 2 parts, but by the way, you have to identify your a sub n. Here, a sub n is the part without the -1 to the n minus 1 power. So e to the 2 over n is the a sub n. We got to check the 2 things. The first, the limit as n goes to infinity of a sub n. We have already done that. Okay, and that again is 1, and AST required this to be a 0 as a requirement for convergence, and that requirement is not met. So again, what this means, what this limit means is that when you expand the series is long enough, when you expand the series long enough, you end up with 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. And this series does not have a definite value. The partial sum, the sequence of partial sum is not convergent. I mentioned this yesterday. Because again, S2 is 0, S3 S3 is 1, S4 is 0, S5 is 1. When you add the terms, you get either 0 or 1 forever. Therefore, no definite value for the sum. Okay, so divergent, we are done. AST does not pass. The series is divergent by AST alternating series test. Good problem. I was looking for a problem just like this one. Thank you. Okay, more questions from the section?
So I just have a general question.
Yeah.
Piggybacking off this, what about the time where we get one? What are the problems where we get one and it's neither conclusive or inconclusive, where we have to do another test?
That's the ratio and the root test.
Okay.
Yeah, for ratio and root test, if the limit of the ratio or root is 1, then the series can diverge or converge. You have to use a different test. It has nothing to do with the nth term test. The nth term test, again, says that if the limit of the sequence, the nth term, is not 0, then you're just going to be adding that non-zero number to itself forever. Therefore, the series is going to diverge.
Yeah, I just was curious about that, kind of unrelated to the problem. Thank you.
Okay, so any more questions from this section? Maybe we could do number 10. 10 is good because 10 is a conditionally convergent series, actually. Okay, and the problem is I'm going from 1 to infinity of square root of n over 2n plus 3, and then there's, of course, a -1 to the n in front. I've seen people factoring this out. I saw people, someone, just one person, put this -1 to the n in front of the summation notation. It's a part of the sum. You guys can't do stuff like that, okay? It's just the sign of the term. So check for absolute convergence. All right, we're gonna do the series of the absolute value of the nth term, which gives you a positive term series, the sum of root n over 2n plus 3. And here again, n starts from 1, goes to infinity. So let's see, what test should we use on this positive term series? You can begin with the nth term test in your head, okay? Look at the limit of the sequence, the limit of the nth term. That limit is 0 anyway. Nth term test is not going to give you any conclusion. The limit is 0 because the degree of the denominator is larger than the power of the numerator. Here the power is 1, the top the power is half. So a sub n goes to 0. Nth term test doesn't say anything. Okay? Yes, we want to do, Ahmed. Yes, we want to do comparison on this for sure. Why do I want to do a limit comparison? I want to do a limit comparison because I can get rid of non-dominant terms and compare to a much simpler series. Okay, we can ignore that 3. If I ignore that 3, I get root n over n. I can simplify that. I end up with a nice piece series. Okay, So we're gonna use limit comparison. Again, I hope you see why. I hope you understood why. Whenever you see a fraction where you can ignore non-dominant terms, limit comparison is the best way to go. Okay, so step one of the limit comparison. We have a sub n root n over 2n plus 3. We say that this is asymptotic to top is just root n, one term on the top, and the bottom 2n is dominant. When you reduce this fraction, you get 1 over n, 1 over 2 to the power of 1 over 2n to the power of 1/2. And this becomes b sub n. This is a p sequence, not a p series. Step 2, you mention, you don't do. Just mention that the limit as n goes to infinity of a sub n to b sub n is equal to 1. And that's because a sub n and b sub n are asymptotic. And then step 3, say what happens to the summation of b sub n. Now, here is what I can bet on the test. People don't write the summation notation. They say this diverges because it's a p series. B sub n is a sequence, it's not a series. Okay? B sub n, as a matter of fact, converges. You see that? If you ignore the summation notation, b sub n 1 over 2 to the 1 over 2n to the half, it's convergent. That sequence goes to 0 because the denominator is increasing. Okay, this sequence goes to 0, it's convergent. But we are talking about the sum of this thing. Sum. It's a series, it's not a sequence, and this sequence is divergent. It's a divergent p series because p is equal to half, and that is less than 1. Okay?
Wait, Professor, did you say it was a sequence, or am I confused?
So if I was saying that some people, they don't write the summation notation for whatever reason, they're rushing through the test, or I don't know why exactly. People forget to write the summation notation. Okay, if you don't write the summation notation, then 1 over 2n to the half is not a series, it's a sequence. It is a sequence. And it's convergent because it goes to 0. But when we put the sum, now it's a series, and that series is divergent. So don't forget to write the summation notation, guys. Some people don't even bother with anything, with writing anything. They put an arrow to that. I swear, I've seen this before. They put an arrow to that and they say convergent or divergent. And they expect a credit. Okay, but again, the summation of this sequence that we chose is divergent because it's a p series. And conclusion, therefore, a sub n, the summation of a sub n, which was root n over 2n plus 3 is divergent. Okay, so here the conclusion is that this series did not absolutely converge. Okay. So you're gonna go ahead and check AST because the series can converge. All right, so again, I'm writing down the series. Here, a sub n is root n over 2n plus 3, and you're gonna check the two requirements. So number one is the limit of a sub n. And we discussed this limit already. This limit is 0. Because again, the power of the numerator is less than the power of the denominator. The denominator grows faster than the top. Okay, don't spend time on that. This limit is from calculus 1 or even pre-calculus. Okay, now next step, you got to show that the sequence is a decreasing or non-increasing sequence. Okay, so what you do is call f of x to be square root of x, or you can call it x to the half, because I'm going to be taking derivatives. I want to write it as a rational power like that, divided by 2x plus 3, and it's on x going from 1 to infinity, because n goes from 1 to infinity, so this is for x larger or equal to 1. Take the derivative, hoping the derivative is negative. I have to use the quotient rule. You can also use the product rule. You can write quotient as a product and do product rule, but I could just do quotient rule on this. Square the bottom. Okay, we're gonna take the derivative of the top, which is 1/2 x to the power of negative 1/2. Times that by the bottom minus top times the derivative of the bottom, which is just 2. Be patient here, guys. I have to show this is negative. You can't just say less than 0 and be done with it. It has to be believable. How is this less than 0? We got to show that. We're not done yet. You got to do some algebra. Unfortunately, you have to do some algebra. To simplify this thing, you would have to, let me see, you would probably want to factor out the GCF. We have this expression and this expression separated by this subtraction. Okay, take out the GCF. The GCF is x with the smaller power. So x to the negative half is the GCF. Take that out. You can also take 1/2 out and get rid of that fraction. Please pay attention, guys. This is algebra. No one likes algebra. I'm gonna take out 1/2 x to the negative half. GCF by definition is x with the smaller power. Okay, so from this expression, this thing is out, so I am left with 2x plus 3. We have now minus. This is very easy. You want to know what goes here. You ask yourself, x to the negative 1/2 times what gives me x to the 1/2? Again, x to the negative 1/2 times what gives me x to the 1/2? Yes, just x, because you have to add when you multiply, you have to add the exponents. So the exponent here has to be 1, so that when you add negative 1/2 and 1, you get 1/2. So x, okay? And then when you take 1/2, when you take half out of 2, you get 4. Again, ask yourself, 1/2 times what is equal to 2? And the answer is 4. Okay, so that's done. Basic algebra, I hope. All right. So again, I can simplify a little bit. You can move this 1/2, you can move the 2 to the denominator. You can move this factor down to the denominator and make the exponent positive. So we have 2x to the half times 2x plus 3 squared. Okay, and on the top, we are left with 2x minus 4x, which is negative 2x plus a3. Okay, so that is the derivative function. This is just the derivative function. And the intention is to show that the derivative function is negative. So typically, if you see a negative in front of the whole function, like the problem we did yesterday, let me go back to that problem. Yeah, you see that we did the derivative, the first derivative sign analysis on this problem yesterday. When I took the derivative and I simplified, I have a negative in front of the whole thing. This whole thing is a positive. The top is positive, bottom is positive. With the negative, the whole thing is less than 0. So it was apparent that the derivative here is negative. Okay, but with this problem, I don't have that. I don't have a negative in front of the fraction. I have a negative 2x plus 3. Okay, in the bottom, I have these factors. These are always positive. This is positive. This is positive because it has a square. So the goal is to show that this thing is negative eventually. Okay, eventually. The derivative function doesn't exactly, Jose. The derivative function doesn't always, guys, listen, please. The derivative function does not have to always be negative. It has to be negative eventually. Starting at some x forward. The sequence has to be negative eventually, starting at some n forward. Okay, so just think about it. Just think about it. You don't have to think too much. If x is more than 3/2, here, just set this less than 0. Set it less than 0 and say when this happens. Okay, so this is less than 0 when the top, negative 2x plus 3, is less than 0. So once more, guys, the bottom is positive. Everything in the bottom is positive. So we don't have to worry about that. Therefore, the whole thing shall be negative if the top is negative. Okay, that's why I said when the top is negative. And then solve this inequality, you get negative 2x less than negative 3. Solve by dividing by negative 2, you get x greater than 3/2. The direction of that inequality changes. So the derivative function becomes negative starting at x of 3/2. And that's what we wanted. We don't want the derivative to be negative for all x in the domain of the function. Okay, it has to be true starting at some x. This could be x greater than 100. That would mean eventually. Okay, so here the conclusion is that a sub n, the sequence function square root n over 2n plus 3 is decreasing for n larger than or equal to 2. Can anybody tell me why I said n larger or equal than 2? It was supposed to be larger than 3/2. Why did I say 2? Why did I change that?
Because in series, it only accounts for like integers, not rational numbers.
Yes. Yeah, exactly. The domain of a sequence is a natural number, is a set of natural numbers. So if this function is decreasing starting at x equal 3/2, then we say the sequence function decreases starting at n equal to 2. Just round up pretty much. And that's what we wanted. Both conditions check for ASC. Okay, so the series is convergent, but it converges conditionally.
Professor, I have a quick question for this problem.
Mhm.
So you know how like the numerator is negative 2x plus 3, and then the whole thing is like less than 0. Can't you just like pull out the negative from the numerator and then put like a negative sign in front of the whole fraction and say it's
But
less than?
then I get what you're saying. So I put the negative in front, and then that becomes a 2x minus 3.
Yeah.
Well, the thing is 2x minus 3 is not always positive.
Okay.
It's not always positive. You're thinking about the last problem, the problem from, yeah, this problem.
Mhm.
The thing is that with the negative in front, the numerator is always positive because you have the sum of squares, the sum of two positives. That's the whole thing is positive on the top. The whole thing at the bottom is also positive because you have a square.
Okay, yeah.
You know what I mean? Yeah. Good problem. Not, yeah. So again, just do a recap. The problem looks simple when you in your mind compare it to other problems, but it took a good 1.5 page, 2 pages of work almost. So again, I check for absolute convergence, drop the -1 to the end. Okay, run whatever test. You see a fraction like that where the top and bottom consist of terms. You want to do limit comparison for sure. Okay, limit comparison to set that the series is not converging absolutely. So you check AST, both requirements. AST passed. The alternating series is convergent, but it's convergent conditionally. Okay, make sure you mention. So conditional convergence is for alternating series. Okay, it's converging conditionally because it's convergent, but it's not absolutely convergent. Just reminding what that means. So again, conditional convergence means that the series is convergent, but not absolutely convergent. Okay. Now, I want to talk about so this was actually in the quiz, one of these problems. I want to go over it again, make sure that you guys understand what's going on. So this is problem 24 in section 11.6 actually. Okay, and it says sum -1 to the n, and then we have this weird 2 to the n factorial over 5 times a times 11 times dot 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 times 3n plus 2. Yeah. So first time I saw a series like this as a student, I was confused because I see these factors in the bottom. There's a pattern among these factors. So I asked myself, why isn't this? Did I get that right? No, this is a 3m plus 2. Why isn't the denominator just a factorial? Why didn't they say, why instead of writing this out, they did not say 3m plus 2 factorial? So let me explain that. Let's write out a few terms of this series, okay? So I'm just gonna expand this. When you plug 1 for n, first term is negative, we get on the top 2, in the bottom, we get 5, okay? When n is 1, in the denominator, we're looking at the first factor. N equal to 1 corresponds to the first factor, which is this 5. And by the way, on the top, 1 factorial is just 1. Next term is positive because when you plug 2 for n, you get -1 squared. On the numerator, we get 2 squared times 2 factorial. 2 factorial, if you want to write that down, that's a 2 times 1. Okay, in the bottom, we get the first 2 factors, 5 times 8. So n equal to corresponds to 2 factors. Next term is negative. Numerator is 2 cubed. And then 3 factorial is 3 to 1. And then in the denominator, we have 5 times 8 times 11. Okay. So again, question or what is confusing about this problem is the fact that we cannot write the denominator as a factorial. Why isn't this just a 3n plus 2 factorial? Because I'm sure a lot of you, almost all of you, or most likely by now, all of you know that we can't write that as a factorial because a factorial, remember guys, factors of a factorial go down by 1 every time, by 1. No matter what kind of factorial you have, anything factorial, n factorial, 2n factorial, 3n plus 2 factorial, 3n minus 10 factorial, the factors of any factorial goes down by 1. Any 2 consecutive factors of factorial differ by 1. These factors do not differ by 1. They differ by 3. So they're not factorials. This is not a factorial. How am I going to write that as factorial? I can't. It makes no sense. Okay, so this is the meaning of the series. All right. So the nth term of the series is described by this thing right here. It's an alternating series, so we're going to check for absolute convergence. All right, and you can again drop the -1 to the end. So here, this is what I'm going to do for short. The summation of absolute value u sub n is this whole thing. Okay, this is just equal to the summation of terms without that -1 to the end. just drop that -1 to the n, you get 2 to the n and factorial over a product of those factors. Okay. Of course, guys, we want to use the ratio test because we are dealing with factors. No other test is suitable. Okay, you don't want to do comparison tests. We do limit as n goes to infinity of a sub n plus 1 divided by a sub n. You can do the ratio test this way. The book presents the ratio test like this: limit as n goes to infinity of absolute value of u sub n plus 1 over u sub n. They do that. So they instead of the book, I know, instead of taking the absolute value of u sub n and rewriting the series as a positive term series, the book skips all that and they do the ratio test in absolute value. They take the limit of the absolute value of the ratio. They kind of try to hit two birds with one stone is what they're trying to do. Okay? But just do it this way if that's confusing. I'm trying to be consistent with notations. So limit as, so here is where you have to be very, very careful, guys. Let me, very, very careful. And I did explain this in the video, and I'm gonna emphasize on it again. So please make sure you pay attention if you haven't watched the video carefully. I wanna write down a sub n plus 1. A sub n plus 1 means that you take the sequence, replace n with n plus 1. So we get 2 to the n plus 1. And factorial now becomes n plus 1 factorial. Okay. This is where things can be a little bit confusing. With this thing, guys, make sure you're listening. With this thing, a sub n plus 1 is gonna have an extra factor. That's what a sub n plus 1 does. It has an extra factor. Okay? We could see that already. See, 2 to the n plus 1 is 2 to the n times 2. See, 2 to the n plus 1, that is an extra factor. N plus 1 factorial is n plus 1 times n factorial. So comparing it to a sub n, this thing has an extra factor of n plus 1. So same thing for the denominator, a sub n plus 1 is gonna be the same as this, but with an extra factor. So you just write down this product, 5 times 8 times 11 times dot, 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 times 3n plus 2. Write that factor. Don't skip it, write it. Okay, you must also, so this is n factors. That's n factors. Now we're gonna have an extra n plus 1 factor. Okay, that n plus 1 factor is 3n plus 1 plus 2. Okay, which is really 3n plus 4. What is 3n plus 5? It's 3n plus 5. Is that right? Yes. 3n, if I multiply that by, you get 3n. Yeah. So just replacing n with n plus 1. Okay. So write the first n factors of a sub n plus 1, and in addition, write the n plus 1 factor. Okay, so that is your a sub n. Again, a lot of people don't write the nth factor, they don't write it. And when they don't write it, things can get a little confusing later. So make sure you write that. Let me just decrease the size a little bit so I can fit everything here. Okay, now we're gonna multiply that by the reciprocal of a sub n. I'm gonna write 2 to the n factorial down here, and then on the top 5, 8. Okay, so that's a sub n plus 1 divided by a sub n is the same as a sub n plus 1 multiplied by the reciprocal of a sub n. Okay. Yeah, so let's try to expand. That's the next step. Expand a sub n plus 1. Rewrite a sub n plus 1. For instance, 2 to the n plus 1, I could write that as 2 to the n times 2. N plus 1 factorial, you could expand that as n plus 1 times n factorial. We did discuss why. And I'm gonna leave the reciprocal of a sub n. Just leave that alone, copy that. Don't do anything to that, just copy that. You're just expanding the factors of a sub n plus 1. So expand that. In the bottom, we have and then that last factor is 3n plus 5. Okay, 3n plus 1. These factors differ by 3. See, 5 and 8 differ by 3. 8 and 11 differ by 3. 3n plus 2 and 3n plus 5, they differ by 3. They go up by 3. Now you're gonna cancel. Okay. Reduce. 2 to the n cancels 2 to the n. That n factorial cancels n factorial. We have all of these factors, all those factors, there are n of them, cancel all of these factors, n of those factors cancel. Okay, so we are now left with a simple expression for the ratio, which is 2 times n plus 1 on the top, and in the bottom we have 3n plus 5. Okay, and we are done. Take the limit. The limit is 2/3. Okay, and this is a number between 0 and 1, which means that the series, this is what you're checking. The sum of the absolute value of the terms converges by ratio tests. Okay, therefore, the series, the summation of u sub n, this series is absolutely convergent. Alexander, question. So what do you mean? Why do we put 3n plus 2 in
in the denominator for
here?
canceling? Yeah.
Well, because as I said here, a sub n plus 1 is going to have the first n factors. These are the first n factors. It has the first n factors in addition to an extra factor, the n plus 1 factor.
Oh, okay. Thank you.
Mhm. And that's it. Could L be infinity yeah, Ahmed, if L is infinity, yeah, it could be infinity, that the series is diverging, yeah. A ratio that goes to infinity tells you the series is just blowing up out of proportion, going to infinity really, really fast, yeah. You're welcome, guys. Have a good day. If you have a question, just stick around.
Thank you, Professor.
Thank you,
No,
Professor.
yeah, you're welcome. L doesn't have to be a number. Limit of the ratio can go to infinity. If that happens, it means the terms of the series get larger really, really fast. So the series is divergent.
And Professor, your office hours today at 9:45.
Yeah.
Okay, perfect.
Professor, I had a quick question.
Yes.
Can we compare answers for the
I
quiz?
did answer the chat.
Oh, okay, thank you.
Ahmed, to answer your previous question, you don't have to mention those laws. The degree of top is less than bottom. If it's a limit from math 7 or math 2, just give the answer. You don't have to justify. Is Ahmed here? No, he's gone. Just talking to myself. You too, Nelson.